Venus rotates in reverse compared to almost every planet in the solar system, and scientists are still working out exactly how it ended up spinning this way after billions of years of evolution. The impossible planet. Deep space is silent, and in that silence, the solar system does not look like anything random or scattered. It looks organized, like everything once came from a single spinning cloud that slowly pulled itself together into order. And out of that process came the Sun in the center and the planets around it, all moving in the same general direction, all sharing the same original spin from that ancient cloud. That is what makes Venus stand out even before you get close to it, because it looks like it refused to follow that shared direction from the very beginning. Like something about it was set on a different path, while everything else stayed aligned. Most planets in the solar system rotate in one direction, and that direction comes from the way the solar system formed, from a massive rotating disk of gas and dust that flattened out over time. And when small pieces inside that disk started sticking together, they carried that original spin forward into the planets we see today. So Earth spins one way, Mars spins the same way, Jupiter spins the same way, and even Saturn follows that same general direction, almost like a rule that was never meant to be broken. But Venus breaks it in a way that is not small or subtle. It is not just tilted or slightly off. It is fully reversed, spinning in the opposite direction from almost everything else around it. If you could stand above the solar system and watch Venus from far away, what you would see is not just a slow or unusual rotation, but a planet turning the wrong way compared to its neighbours, like a wheel spinning against the flow of traffic. The strange part is that nothing in the formation story of the solar system clearly predicts this, because everything about the early system points toward a shared direction of spin. Not a reversal, not a contradiction, not a planet going against the pattern that built it. And then there is the detail that makes it even harder to accept at first. The kind of fact that forces you to stop and replay it in your mind. Because Venus does not just spin in the opposite direction, it spins extremely slowly. One full rotation takes about 243 Earth days, which is longer than the time it takes Venus to go around the Sun, which is about 225 Earth days. That means a single day on Venus, from one sunrise to the next, does not follow a normal rhythm, like Earth or Mars. On Venus, time behaves in a way that feels almost disconnected from what we expect, because the planet itself turns so slowly that its own rotation cannot keep up with its orbit. So if you were somehow standing on Venus and could survive the conditions there, which already pushes reality into extreme limits, you would not see the sun rise in the east like on Earth. You would see it rise in the west, slowly, almost painfully slow, as if the sky is moving in reverse, and then it would set in the east. That single detail alone is enough to make Venus feel unfamiliar in a very direct way, because it changes something that feels universal on Earth, the direction of the sky itself. But the strangeness does not stop at rotation. The surface of Venus is hidden under a thick atmosphere made mostly of carbon dioxide, so dense that it acts like a heavy blanket wrapped around the entire planet, trapping heat and building pressure far beyond what a human body or any Earth-built machine could survive for long. The temperature on the surface reaches levels high enough to melt lead, and the pressure is so strong that it feels like being deep under Earth's oceans, but even more intense, constant, and crushing. Above this surface sits a layer of clouds made of sulfuric acid, not water, not ice, but acid droplets floating in a thick global haze that never clears. From space, Venus looks calm and bright, almost beautiful in a simple way, because the cloud layer reflects sunlight strongly, making it one of the brightest objects in the night sky. But that brightness hides everything happening below, and it hides the fact that the planet underneath is extreme in every direction at once. Heat, pressure, and atmosphere all working together in a way that has no close match among the rocky planets of the inner solar system. Now place all of this together, the reverse spin, the extremely slow rotation, the thick atmosphere, the crushing surface conditions, and you start to see why Venus is not just another rocky planet with a small difference. It stands out as something that behaves against expectation at multiple levels at once. It is not only spinning the wrong way, it is also doing it slowly, while wrapped in a dense atmosphere that moves in a completely different pattern from the surface below it. And this is where the real question starts to take shape, because none of this should naturally happen if all planets form from the same rotating disk of material. If everything began from a single spinning cloud, then the direction of spin should be mostly shared, even if there are small differences or tilts along the way. So how does a planet end up fully reversed, not just slightly off, but completely opposite in rotation from its neighbours? How planets normally get their spin. Before you even think about Venus spinning the wrong way, you have to understand what normal even means in space, because nothing in space starts out with planets already spinning neatly like they do today. Everything begins in a messy, wide, slowly changing cloud of gas and dust that stretches across huge distances. And inside that cloud there is no fixed direction at first, no clear structure, just motion that slowly builds into something more organized over millions of years. That cloud is what scientists call a protoplanetary disk, but the name is less important than what it actually is, which is a huge spinning flat cloud made mostly of hydrogen and helium with tiny bits of dust mixed inside it. And this cloud exists because a star is forming in the middle of it, in our case the Sun. And as gravity pulls everything inward, the cloud starts to flatten. Not because it wants to, but because of how motion works when things collapse and spin at the same time. To understand this properly, imagine something simple but real, like a large cloud of dust in space that is slowly shrinking under its own gravity. As it shrinks, it does not fall straight inward like a stone, because every particle inside it already has some motion, even if it is very small. And once gravity pulls everything closer together, that small motion becomes more important, and the whole cloud starts to spin faster as it gets smaller, just like an ice skater pulling in their arms while spinning. This is where the idea of angular momentum comes in, but it does not need to sound complicated, because in simple terms it just means that when something is spinning in space, it keeps spinning unless something strong changes it, and the total amount of spin in a system stays the same, unless outside forces interfere. So when the early solar system clouds started collapsing, its original slow spin did not disappear. It just got concentrated into faster motion as everything got closer together. That is why the solar system does not form randomly in all directions, because the whole cloud already had a general spin before planets even existed, and when it flattened into a disk, that spin turned into a clear direction of rotation, and everything that formed inside that disk inherited that direction in some way, like pieces of a spinning wheel that all follow the same turn. This is why most planets spin in the same direction today, because they were born inside that same rotating structure, and as small pieces of dust collided and stuck together, they formed larger and larger bodies called planetesimals, and those planetesimals kept merging until they became full planets, and each step of that growth carried forward the original motion of the disk. So when you look at Earth, Mars, Jupiter, Saturn, Uranus, in terms of orbital direction, they all move around the Sun in the same general direction because that is the direction the disk was spinning. And their rotation, meaning how they spin around their own axis, also mostly follows that same inherited direction, because when planets form, they are not placed gently into space. They are built through endless collisions, and those collisions usually do not cancel out the original spin. They reinforce it or slightly adjust it. To see why this matters, you can think of the early solar system not as a clean set of planets waiting in order, but as a violent construction zone where thousands of rocky and icy bodies were crashing into each other, sticking, breaking, melting and reforming, and every collision carried energy, and that energy often turned into spin. So as planets grew, they were constantly being pushed, twisted and spun, but always inside the same overall direction that came from the disk. Now Earth is a good example of what normal rotation looks like after all of this settles down, because Earth rotates once every 24 hours, and it does so in a stable, consistent way that has lasted billions of years with only small changes. And that rotation direction matches the general direction of the solar system's original disk. So when the Sun rises on Earth, it rises in the east because Earth spins in a specific direction relative to space. And that direction is not random, it is inherited from formation. What makes Earth's rotation especially important here is not just that it spins, but that it spins in a stable way compared to many other bodies in space, because once a planet reaches a certain balance between its internal structure and external forces, its rotation becomes steady. And while it can slow down slightly over time due to tidal forces, like the Moon pulling on Earth's oceans, the direction of spin does not usually reverse. Because reversing a planet's spin is not something that happens easily. It requires extreme energy or long-sustained external forces acting in one direction. This is where most planetary behavior follows a pattern. Because in space, rotation is not usually something that flips completely, it is something that evolves gradually. And even when planets are affected by strong events, they tend to tilt their axis or speed up or slow down, rather than completely reverse their spin direction. Which is why Venus stands out so strongly later in the story. There are a few known ways a planet's rotation can change, and they all involve either strong impacts, long gravitational interactions, or internal atmospheric effects, but even these usually do not fully reverse spin unless conditions are extreme or repeated over long periods of time. One of the most dramatic causes is a giant impact, where a large body crashes into a planet during its early formation stage, and this can change the planet's spin dramatically. Because the energy involved is huge, and depending on the angle and speed of the impact, it can tilt a planet's axis or even slow down or speed up rotation significantly. And in some rare cases, it can reverse the spin direction. But this is not common, and it requires very specific conditions. Another influence is tidal interaction, which comes from gravitational forces between a planet and another body, usually a star or a large moon, and over very long timescales, these forces can slow rotation, lock rotation into a pattern, or slightly reshape how the planet spins. But again, these effects are usually gradual and predictable, not sudden reversals. There is also atmospheric influence, where a thick atmosphere can transfer energy to a planet's surface over time, especially if the atmosphere moves in fast global wind patterns, and this can slowly affect rotation. But for rocky planets like Earth, this effect is extremely small compared to the planet's mass and rotational inertia. So when you put all of this together, you get a clear baseline picture of what normal rotation looks like in planetary systems. Planets form inside a spinning disk, they inherit a general direction of motion. They grow through collisions that mostly preserve that direction. And over time, they settle into stable rotations that usually remain consistent for billions of years, unless something very large disturbs them. That is why the solar system appears ordered when you look at it from a distance, because most of its major bodies follow this shared history of formation. And even though there are variations in tilt, speed, and axial wobble, the overall pattern stays consistent enough that it looks like everything came from a single, shared origin, which it did. But even within this framework, there are small exceptions and unusual cases scattered across space. And those exceptions are not random. They usually have explanations tied to specific events, like a massive collision, a gravitational capture, or a long-term resonance with another object. And those cases are important because they show that while the general rules of planetary rotation are strong, they are not absolute. For example, Uranus rotates in a way that is extremely tilted compared to most planets, almost like it was knocked over during formation, likely by a massive impact. And Pluto has unusual orbital behavior due to its resonance with Neptune. And some moons in the solar system rotate in ways that are locked to their planets due to tidal forces, meaning they always show the same face. But even in all these cases, the fundamental direction of spin is not fully reversed in the same clean way that Venus shows. And that is where the key difference begins to stand out, because Venus is not just slightly tilted or slightly altered, it is fully reversed compared to the standard direction. And that is not something that fits easily into the usual patterns of planetary change. To make this clearer, think again about Earth as the reference point. Earth rotates in one direction, and that direction matches the general spin of the solar system. So when you move outward to Mars or inward to Mercury, you still see that same general alignment. But when you reach Venus, that alignment breaks in a direct and unmistakable way. And what makes this more interesting is that Venus is not a strange object from outside the system. It is not an interstellar capture. It formed in the same region as Earth and Mars, from the same disk, under the same conditions, which means it should have started with the same general direction of spin. Yet something changed it so completely that it now rotates in the opposite direction. This is where the baseline understanding becomes important, because without knowing what normal planetary spin looks like, Venus can seem like just another odd object in space, but when you compare it to the structure of how planets are built, it becomes something much more specific, a direct contradiction to the expected outcome of planetary formation in a rotating disk. And that contradiction is what drives everything that comes next. First, discovery of Venus's rotation. For most of human history, Venus looked simple from Earth, just a bright point of light in the sky that moved with steady patience across the night and morning, sometimes called the morning star and sometimes the evening star, depending on when it appeared. And early observers had no real way of knowing what was happening on its surface or how the planet itself was moving, because all they could see was a bright glow wrapped in constant cloud, with no surface features, no shadows, and no clear detail to track. Even with early telescopes in the 17th and 18th centuries, when astronomers like Galileo first turned their instruments toward Venus, what they saw was still frustratingly limited, because unlike Mars or the Moon, which show visible surface markings that shift with time and reveal rotation, Venus remained smooth and bright, almost like a glowing ball with no visible texture, and this made it extremely difficult to measure anything about its spin or its surface behavior. At that time, astronomers were already beginning to understand that planets rotate, because they could clearly observe the movement of features on Mars and the changing shadows on the Moon, and from those observations they could calculate rotation periods and build a growing understanding of how planets behaved. But Venus refused to cooperate with this method, because its thick cloud layer completely hid its surface from direct optical observation, blocking any attempt to track landmarks over time. This cloud cover is one of the most important reasons why Venus remained mysterious for so long, because it is not just a thin layer of clouds like Earth sometimes has. It is a global, permanent atmosphere made mostly of carbon dioxide, with clouds of sulfuric acid floating high above the surface, and this thick layer reflects sunlight so strongly that almost no visible light from the surface ever escapes, which means that for centuries, Venus was essentially a blank screen in the sky, revealing nothing about its rotation or surface features. Because of this limitation, early scientists were forced to rely on indirect reasoning and speculation. And for a long time, there was a strong assumption that Venus might be similar to Earth in many ways, because it is close in size, close in distance compared to other planets, and often called Earth's twin in early astronomy. And this idea influenced how scientists thought about its rotation as well, leading many to assume that Venus would rotate in a similar way to Earth, with a roughly 24-hour day and a consistent east to west cycle. But assumptions are not measurements, and without direct evidence, there was no way to confirm how fast Venus rotated or even which direction it spun, and this uncertainty lasted for centuries, making Venus one of the least understood major planets in the solar system, despite being one of the brightest and most visible objects in the sky. As telescopes improved in the 19th century, astronomers began searching for subtle clues, such as slight differences in brightness or temperature patterns across Venus's surface, hoping that careful observation might reveal rotation indirectly. But even these efforts were blocked by the thick atmosphere, because the clouds move constantly and unpredictably, creating shifting patterns that do not match the surface beneath them, which means that any attempt to track rotation through cloud movement alone leads to misleading results. There were also early ideas that Venus might be tidally locked to the Sun, meaning one side always faced the Sun, while the other remained dark, similar to how the Moon is locked to Earth. And this idea made sense at the time because Venus is closer to the Sun than Earth and experiences stronger gravitational influence. But later observations showed that this was not the case, because temperature readings and later radar data proved that Venus rotates, even if it does so very slowly and in an unusual direction. For a long time, the biggest limitation was simple technology, because visible light telescopes cannot see through thick clouds, and without being able to see the surface, there was no direct way to measure rotation. So Venus remained a mystery wrapped in brightness, and even as astronomy advanced into the early 20th century, the basic question of how Venus rotated was still unanswered. The real breakthrough began when scientists started using radio waves instead of visible light, because radio waves can pass through thick cloud layers, and this opened a completely new way of studying planets, allowing researchers to look beneath the cloud cover of Venus for the first time in history. And this shift did not just improve observations, it completely changed what was possible in planetary science. Radio astronomy became a powerful tool in the mid-20th century, and one of the most important techniques developed was radar mapping, where scientists would send radio signals toward a planet and measure the reflection that came back, and by analysing the timing and frequency changes in the reflected signals, they could determine not only surface features but also motion, including rotation speed and direction. This method was revolutionary for Venus, because it bypassed the cloud problem entirely, allowing scientists to see the surface indirectly for the first time. And early radar experiments began to reveal surprising results, showing that Venus did not behave like a simple Earth-like planet, but instead had a rotation that was extremely slow compared to Earth, and possibly in a different direction than expected. One of the key places where this work advanced was the Arecibo Observatory, a massive radio telescope built to study planetary surfaces and atmospheric behaviour using radar signals, and from this facility, scientists were able to bounce radio waves off Venus and measure how the returning signal shifted depending on the planet's rotation. And these measurements slowly built a clearer picture over time. At the same time, the Soviet space program launched a series of missions called Venera, designed specifically to study Venus up close, and while many of these missions were focused on landing on the surface or passing through the atmosphere, they also provided important data about wind patterns, atmospheric density, and surface conditions, which helped refine models of how Venus might be rotating beneath its clouds. As radar data improved, scientists began to notice something unusual, because instead of showing a simple Earth-like rotation, Venus appeared to rotate extremely slowly, and the direction of that rotation seemed to go against the expected pattern based on the solar system's general spin direction, which was the first serious hint that Venus might be rotating in reverse. At first, these results were treated with caution, because the idea of a planet the size of Venus spinning backward did not fit easily into existing models of planetary formation, and scientists carefully rechecked their data, looking for errors or alternative explanations, because such a result would require a major rethink of how planetary systems evolve. But as more radar observations were collected from different facilities and different teams, the pattern became clearer, and the slow rotation was confirmed repeatedly, and with enough consistency that it could no longer be dismissed as measurement error or atmospheric interference. And this led to one of the most surprising conclusions in planetary science at the time. Venus was not only rotating slowly, it was rotating in the opposite direction from most planets in the solar system, meaning that if you could somehow observe its poles from above, it would appear to spin the other way compared to Earth, Mars, Jupiter, and Saturn's. And this was a direct contradiction to earlier expectations based on how the solar system formed. This discovery created a strong tension in the scientific community, because the assumption had always been that planets forming in the same rotating disk would naturally share the same general spin direction. And while exceptions were known, such as tilted axes or unusual resonances, a full reversal was something far more extreme and much harder to explain with simple formation models. The reaction was not immediate acceptance, because science at this level moves carefully, especially when results challenge long-standing models, and researchers spent years testing different explanations, including the possibility that Venus had been struck by a massive object early in its history, or that long-term atmospheric forces had slowly changed its rotation, or even that measurement methods were still missing something important. But as technology improved further and more detailed data came in from spacecraft flybys and orbiters, the evidence became stronger, and the idea that Venus truly rotates in a retrograde direction became widely accepted, even though the exact cause remained unclear. And this shift marked a major turning point in how Venus was understood. What makes this discovery especially important is not just the fact that Venus spins differently, but the way it was discovered, because it shows how limited human observation once was, how dependent early astronomy was on visible light alone, and how a planet can remain hidden in plain sight for centuries, even when it is one of the brightest objects in the sky. And even after the rotation was confirmed, the deeper question remained open, because knowing that Venus spins backwards is not the same as knowing why it does so, and that unanswered question became the starting point for deeper investigation into the planet's past, its atmosphere, and the violent early history of the solar system itself, where small changes in motion could have led to outcomes as extreme as the one seen on Venus today, measuring a planet hidden in clouds. For a long time, Venus was not just hard to study, it was almost like it was refusing to be studied at all, because no matter how powerful Earth-based telescopes became, the surface stayed completely hidden behind a thick, permanent cloud layer that never broke, never cleared, and never gave even a small glimpse of what lay underneath. And this single fact changed everything about how scientists had to approach the planet, because it meant that normal observation methods simply did not work. Optical telescopes, which rely on visible light, were the first and most obvious tools used to study planets, and they worked well for many other objects in the solar system. Because Mars shows surface markings, Jupiter shows cloud bands, Saturn shows rings, and even Mercury can show phases and surface changes over time. But Venus was different, because its atmosphere reflects almost all visible light back into space, creating a bright, smooth glow that hides every detail beneath it. And no matter how much magnification was used, the result stayed the same, a featureless white-yellow disk that revealed nothing about rotation or surface structure. This failure was not due to poor technology, but due to the physical nature of Venus itself. Because the clouds are not thin or temporary, they are made of dense layers of carbon dioxide gas with thick sulfuric acid droplets floating high above the surface. And this structure scatters light in every direction, preventing any direct view of the ground, which means that even the most advanced optical systems of the time could not break through the barrier. Because of this limitation, scientists had to think differently, and instead of relying on light, they turned to radio waves, which behave in a very different way. Because radio waves can pass through thick clouds without being scattered as much, and this opened a completely new method of planetary study that did not depend on seeing the surface directly, but instead used signals and reflections to build a picture of what lies below. This method is called radar mapping, and the basic idea is simple, even if the technology behind it is complex, because scientists send a powerful radio signal from Earth toward Venus, and when that signal hits the planet's surface, it bounces back. And by measuring how long it takes for the signal to return, they can calculate distance, and by analyzing how the signal changes as it comes back, they can learn about motion, shape, and even rotation. At first, this method was used just to confirm that Venus had a solid surface beneath its clouds. But as the technology improved, scientists realized that the returning signals carried much more information than expected, because the surface of Venus is not perfectly smooth. It has large plains, mountains, and volcanic regions, and as the planet rotates, different parts of the surface move toward or away from Earth, slightly changing the frequency of the returning radio waves. This is where a key idea called Doppler shift becomes important, and it is a simple but powerful effect, because when something is moving towards you, its signal becomes slightly compressed, and when it moves away, the signal stretches slightly, and this change can be measured very precisely, allowing scientists to track motion even across millions of kilometers of space. And when applied to Venus, this effect allowed researchers to detect how fast different parts of the surface were moving as the planet rotated. By combining radar timing with Doppler shift measurements, scientists slowly began to build a clearer picture of Venus's rotation. But the process was not fast or simple, Because the signals were weak, the technology was still developing, and the data had to be carefully filtered to remove interference from Earth's atmosphere and other sources. So each measurement required careful repetition and confirmation before any conclusion could be trusted. One of the major places where this research advanced was the Arecibo Observatory in Puerto Rico, which was one of the most powerful radio telescopes ever built. And it played a major role in studying Venus, because its large dish could send strong radar beams toward the planet and detect very small changes in the returning signals. And over time, repeated observations from Arecibo helped scientists refine their understanding of Venus's rotation speed and direction. At the same time, space agencies were no longer limited to Earth-based observation, because the space age had begun, and spacecraft could now travel directly to Venus, carrying instruments that could measure conditions inside its atmosphere and sometimes even reach its surface. And this changed everything, because instead of relying only on signals bouncing off the planet, scientists could now collect direct data from within its environment. The Soviet Venera program became one of the most important sources of this direct information, because it sent multiple probes into Venus's atmosphere and even landed on the surface under extreme conditions. And while many of these landers survived only for short periods due to the intense heat and pressure, they still managed to transmit valuable data back to Earth, including temperature readings, pressure levels, and atmospheric movement. These missions confirmed what radar had already suggested, that Venus rotates extremely slowly and in a direction opposite to most planets in the solar system. And while the landers were not designed specifically to measure rotation directly, the data they collected helped support the broader models built from radar observations, because they provided ground-level confirmation of atmospheric motion and surface conditions that matched the slow, unusual spin pattern. As more spacecraft visited Venus, including orbiters from both the Soviet Union and later NASA missions, the measurements became more precise, because orbiters could track the planet continuously over long periods of time, observing how surface features moved relative to fixed reference points in space. And this allowed scientists to refine the rotation period with much greater accuracy than before. Early estimates of Venus's rotation were uncertain, with different teams reporting slightly different values depending on the method used. But as radar and spacecraft data improved, a clear number began to emerge, showing that Venus takes about 243 Earth days to complete one full rotation around its axis, which is extremely slow compared to Earth's 24-hour cycle, and this slow rotation became one of the defining features of the planet. But what made this result even more surprising was not just the slow speed, but how it compared to Venus's orbit around the Sun, because Venus takes about 225 Earth days to complete one full orbit, meaning that its day, defined as one full cycle of sunrise to sunrise, is actually longer than its year, which creates a situation that does not exist anywhere else in the inner solar system in the same way. This means that if you were standing on Venus and could survive its surface conditions, you would experience a day-night cycle that does not follow Earth-like patterns, because the planet's slow backward rotation, combined with its orbit around the Sun, creates a cycle where the Sun appears to move across the sky in a very unusual way, rising in the west and setting in the east, but doing so at an extremely slow pace, taking many Earth days to complete even a small movement. This discovery was not something that came from a single moment or a single mission. It was the result of decades of gradual improvement in technology, repeated observations, and careful confirmation across different methods. Because at every stage, scientists needed to rule out errors, refine their models, and compare results from different sources before accepting the final values. What makes this process important is not only the final numbers, but the way those numbers were built, because each stage added a new layer of understanding, starting from optical observations that could not see the surface at all, moving to radar signals that could penetrate the clouds, then to Doppler measurements that revealed motion, and finally to spacecraft data that confirmed the full picture with direct measurements from the planet's environment. At every step, there was uncertainty, because Venus did not behave like a simple object that could be measured once and understood completely. Instead, it required repeated observation under different conditions, using different tools, each one correcting and improving the last, until a consistent pattern finally emerged. Even then, the results did not fit easily into existing expectations, because scientists originally assumed Venus would rotate in a similar way to Earth, based on how planets form in a rotating disk, but the data showed something completely different, a slow, reversed rotation that forced researchers to rethink not just Venus itself, but the range of possible outcomes for planetary formation in general. The strange details of Venus's rotation. Venus does not just spin in a different direction from most planets. It behaves in a way that breaks expectations at multiple levels at the same time. And once scientists finally measured it properly, the full picture was not just surprising, it was layered with more strange details that did not fit neatly into simple explanations. Because the deeper you look at how Venus rotates, the more it starts to look like two different systems are sharing the same planet, one inside the surface and one in the atmosphere, moving at completely different speeds and even in different patterns. The first thing to understand clearly is what retrograde rotation means, because this is the core of the entire mystery, and it is simple in idea but powerful in effect, since most planets in the solar system rotate in the same direction as they orbit the Sun. Meaning, if you could look down from above the solar system, you would see most planets spinning counterclockwise. But Venus does the opposite. It rotates clockwise, which is what scientists call retrograde rotation, meaning its spin is reversed compared to the general direction set by the original spinning disk that formed the planets. This reversal is not a small adjustment or a slight tilt in direction. It is a full change in spin direction, and that is what makes Venus stand out so strongly. Because while many planets can have tilted axes or slightly different speeds, they still follow the same general spin direction. But Venus breaks that shared pattern completely, and that immediately raises questions about what kind of forces acted on it in the past to create such a change. The second detail that makes Venus even more unusual is how slow its rotation is, because one full spin of the planet takes about 243 Earth days, which is longer than its year, meaning it takes more time to rotate once on its axis than it takes to go around the Sun. And this creates a situation that feels completely unfamiliar compared to Earth, where one day is clearly shorter than 1 year, and the cycle of sunrise and sunset follows a predictable rhythm. On Venus, this slow rotation means that if you could observe a fixed point on the surface over time, it would move across space at an extremely slow pace, almost like the planet is barely turning at all. And this slow motion is not just a small detail. It affects everything from how heat spreads across the surface to how the atmosphere interacts with the ground. Because when a planet rotates slowly, one side can stay exposed to sunlight for very long periods, changing temperature patterns in extreme ways. But even this slow rotation is only part of the story, because Venus also has a very unusual axial tilt, which is the angle at which a planet's rotation axis is leaning compared to its orbit around the Sun. And on Earth, this tilt is about 23 degrees, which is why we have seasons. But Venus is almost upright, with a tilt of about 177 degrees when measured in a way that reflects its retrograde spin, which means it is almost completely flipped in terms of rotation direction while still staying nearly vertical in terms of axis angle. This combination creates a confusing situation, because normally when planets have unusual spin behavior, it often comes with a strong tilt, like Uranus, which is almost rolled onto its side due to a likely massive impact early in its history. But Venus does not show that kind of extreme tilt. Instead, it stays nearly upright while spinning in reverse, which makes its rotation pattern even harder to explain using simple collision models alone. When you compare Venus to Mercury, another inner planet with unusual rotation behavior, the differences become even more interesting. Because Mercury is locked in what is called a spin-orbit resonance, meaning it rotates 3 times for every 2 orbits around the Sun, which creates a very stable but unusual pattern caused by the strong gravitational pull of the Sun. And this is very different from Venus, which does not follow a neat resonance pattern, but instead rotates slowly and in reverse without being locked into a simple ratio with its orbit. Mercury's behaviour can be explained largely by tidal forces over long periods of time, where the Sun's gravity slowly shaped its rotation into a stable pattern. But Venus does not fit this same explanation because even though tidal forces from the Sun do affect it, they do not fully explain why its rotation is reversed in the first place, which means there must be other factors involved in shaping its current motion. Another important detail that often causes confusion is the difference between a solar day and a sidereal day, because these two measurements describe different ways of tracking rotation, and on Venus, this difference becomes especially important due to its slow and reverse spin. A sidereal day is the time it takes for a planet to complete one full rotation relative to distant stars, while a solar day is the time it takes for the Sun to return to the same position in the sky. And on Earth, these two values are very close, both around 24 hours, but on Venus, they are completely different because of its slow rotation and its retrograde motion. On Venus, the sidereal day is about 243 Earth days, meaning one full spin relative to the stars takes that long. But because Venus is also orbiting the Sun at the same time, the solar day, which is the cycle of sunrise to sunrise, becomes about 117 Earth days, which is still extremely long compared to Earth. And this creates a strange rhythm, where the Sun appears to move very slowly across the sky in the opposite direction compared to Earth. This means that if you were standing on Venus and could observe the sky, the Sun would rise in the west and move slowly across the sky over many Earth days before setting in the east, and then it would take even more time before the same cycle repeats, which creates a day-night pattern that is completely different from what we experience on Earth and almost every other planet in the solar system. But one of the most surprising and least intuitive details about Venus is not just its surface rotation, but the behavior of its atmosphere. Because while the planet itself rotates extremely slowly, the upper atmosphere moves much faster, creating a phenomenon known as atmospheric superrotation, where the clouds surrounding Venus circle the planet far more quickly than the solid surface below. In simple terms, this means that the atmosphere of Venus is not moving at the same speed as the planet itself. Instead, it is racing around it, completing a full circuit in about 4 Earth days, which is extremely fast compared to the 243-day rotation of the surface. And this creates a situation where the clouds are constantly moving across the sky at high speed while the ground beneath them turns almost imperceptibly. This superrotation is one of the most unusual atmospheric behaviors in the solar system, because on Earth, the atmosphere generally rotates with the planet, even though winds and storms move within it. But on Venus, the entire atmosphere behaves like a separate, fast-moving system that is only loosely connected to the slow rotating surface below. Scientists believe this happens because of strong heating from the Sun, combined with the dense atmosphere of carbon dioxide, which creates powerful wind patterns high in the cloud layers. And over time, these winds have built up a global circulation pattern that moves much faster than the planet's rotation. But the exact process that maintains this speed over long periods is still not fully understood. What makes this even more complex is that the surface of Venus is so slow that it barely influences the atmosphere in comparison. So instead of the ground controlling the air dominates the motion patterns, which is almost the opposite of what happens on Earth, where surface rotation strongly shapes atmospheric movement. So when you put all these details together, the retrograde spin, the extremely slow rotation, the near-zero axial tilt, the difference between solar and sidereal days, and the fast-moving atmosphere, Venus stops looking like a simple planet with one unusual feature, and instead looks like a system where different layers are behaving almost independently from each other, while still being tied together by gravity and heat. The leading theory, giant impact hypothesis. When scientists try to explain why Venus spins in the opposite direction, they always come back to one main idea, and that idea is not simple at all, because it takes us back to the early solar system, a time when nothing was stable, when planets were still forming, still growing, still colliding with other bodies that were almost the same size as them in some cases. And space was not a calm system of clean orbits, but a crowded environment full of violent impacts that could change the shape and motion of a planet in a single event that lasted only hours but reshaped history for billions of years. The giant impact hypothesis starts from this early chaos, because during the formation of the solar system, there were many large bodies called planetary embryos, and these were not small rocks. They were almost planet-sized objects, each one moving through space with its own orbit, its own spin, and its own direction. And as gravity pulled everything together, these bodies often crossed paths and collided, sometimes merging, sometimes breaking apart, and sometimes completely changing each other's rotation and structure. To understand how this could affect Venus, you need to imagine a growing planet in its early stage, still forming its core, still gathering material from surrounding space, and still being hit by other large bodies that are also forming at the same time. And when one of these large bodies strikes another, the energy released is enormous, far beyond anything we see in modern times on Earth, because there is no stable system yet, just a field of moving mass and gravity pulling everything inward. Now, in the giant impact idea, Venus did not simply form and settle into a stable rotation. Instead, it was struck by one or more massive objects during its early life, and depending on the size, angle, and speed of those impacts, the planet's rotation could have been dramatically altered, because when a large object hits a planet, it does not just leave a crater, it transfers momentum, which is the same thing that controls how rotation works in space. And if that momentum is strong enough and in the right direction, it can slow down, speed up, tilt, or even reverse the spin of the planet. This is where the idea of full reversal becomes possible in theory, because if Venus was spinning in one direction early on, and then it was struck by a large enough object moving in the opposite direction, the force of that impact could counteract the original spin. And if the impact is strong enough and not perfectly centered, it could not only stop the original rotation, but push the planet into spinning the opposite way, effectively flipping its direction of spin. But this is not a simple switch, because reversing a planet's rotation is extremely difficult, and it requires very specific conditions. The impactor has to be large enough, the angle has to be just right, and the timing has to match a period when the planet is still forming and not yet stabilized. Because once a planet settles into a stable rotation, it becomes much harder to change its spin direction completely. Scientists study this idea using computer simulations, where they recreate early solar system conditions by modeling planets and planetary embryos moving under gravity. And then they simulate collisions at different angles and speeds to see what happens to rotation. And these simulations show that under certain conditions, a planet like Venus could indeed have its rotation slowed, tilted, or even reversed by a massive impact, especially if the impact happens early enough in its formation when the planet is still partially molten or not fully rigid. In these models, the key factor is angular momentum, which is the measure of rotational motion. And when two large bodies collide, their angular momentum combines, meaning the final spin depends on both original motions plus the effect of the impact. And if the incoming object has enough opposite angular momentum, it can cancel out the original spin and push the planet into a new rotation direction. However, even in simulations where reversal is possible, it is not common, because the conditions are very narrow, and most impacts tend to tilt or slightly change rotation rather than fully reverse it, which means that while the giant impact hypothesis is a strong candidate for explaining Venus's retrograde spin, it is not a guaranteed or simple outcome of planetary formation. There is also another important detail that comes from these simulations, which is that after a massive impact, a planet does not immediately settle into a stable rotation, because the surface and interior are heavily disturbed, and the planet can take a long time to stabilize, during which additional smaller impacts or gravitational effects from the Sun could further adjust its spin, meaning that Venus's current rotation might be the result of multiple events layered over time rather than a single collision. But even though the giant impact hypothesis explains how Venus could have been flipped, it still leaves important gaps, because when scientists compare Venus to the expected results of such a collision, several things do not fully match, and these mismatches are part of why the theory is not considered complete. One of the biggest problems is that Venus has retained a very thick atmosphere, even though a giant impact strong enough to reverse rotation would likely have been powerful enough to strip away a large portion of its atmosphere, especially in the early solar system when impacts were more energetic and planets were still forming their gas envelopes. So scientists have to explain how Venus managed to keep such a dense atmosphere after a potentially catastrophic event. Another issue is the extremely slow rotation of Venus, because while a giant impact can reverse spin, it does not naturally explain why the planet rotates so slowly today, since you would expect a reverse spin to still have significant speed, unless something else acted on it afterward to slow it down over time. And this leads scientists to consider additional processes such as tidal forces from the Sun or long-term atmospheric effects that could have gradually reduced rotation speed after the initial impact. Then there is the question of axial tilt, because if Venus experienced a major impact, you might expect it to have a more extreme tilt like Uranus, which is thought to have been knocked over by a massive collision. But Venus does not show such an extreme tilt. Instead, it remains almost upright, which suggests that either the impact was different in nature or that later processes corrected the tilt over time, bringing it back closer to vertical even after a large disturbance. This combination of features creates tension in the theory because the giant impact hypothesis works well as a general mechanism for changing spin direction. But it does not fully explain the full set of observed features we see on Venus today, especially when all details are considered together, including rotation speed, atmospheric thickness, and axial orientation. Because of this, scientists often combine the giant impact idea with other processes, such as atmospheric torque and solar tidal effects, where the thick atmosphere of Venus interacts with solar heating to create long-term forces that slowly affect rotation. And the Sun's gravity adds another slow but constant influence that can gradually change spin over billions of years, meaning that Venus's current state may not be the result of a single event, but a long chain of events starting with an impact and followed by continuous slow changes. Even with all of this, the giant impact hypothesis remains the most widely accepted starting point for explaining Venus's retrograde rotation, because it is one of the few mechanisms powerful enough to reverse a planet's spin direction in a realistic way. And it fits within what we know about the early solar system, where collisions were common and planetary growth was not a smooth process, but a chaotic series of interactions that constantly reshape planets as they formed. What keeps this theory active in scientific discussion is not just its strengths, but its limitations, because every missing piece becomes a focus for further research, including improved simulations, better atmospheric models, and future missions to Venus that might help scientists understand how its internal structure and surface history connect to its unusual rotation. And each new piece of data has the potential to either support or challenge the idea that a massive early collision set Venus on its reversed path, the atmospheric torque theory. Venus has one of the thickest atmospheres in the solar system, and that single fact changes everything about how the planet behaves, because this is not a thin layer of gas sitting above a rocky surface like on Earth. This is a deep, heavy blanket of carbon dioxide that stretches far upward and presses down with extreme force on the surface. And when you combine that with constant solar heating, you get a system that is always moving, always shifting, and always carrying energy around the planet in large global patterns that never fully stop. To understand why this matters for rotation, you have to picture Venus not as a simple solid ball spinning in space, but as a planet wrapped in a massive moving fluid layer, because the atmosphere is so dense that it behaves almost like a slow ocean of gas covering the entire planet. And when sunlight hits this system, it does not heat it evenly. It creates differences in temperature between regions, and those differences create pressure changes, and pressure changes always lead to motion in fluids, which means wind starts forming at a global scale. The Sun plays a direct role in this process because Venus is closer to the Sun than Earth, so it receives more concentrated solar energy. And even though its thick clouds reflect a large portion of sunlight back into space, the energy that does enter the atmosphere gets trapped and redistributed in complex ways, causing large-scale circulation patterns to form high above the surface, where the air is less dense but still extremely active. These circulation patterns are not small local winds like storms on Earth. They are planet-wide systems that wrap around Venus, forming continuous movement belts that carry atmospheric mass across long distances. And because the planet rotates very slowly, these winds are not simply moving with the surface. They are moving independently, driven mainly by solar heating rather than surface motion. This is where the key idea begins to form, because when you have a fast-moving atmosphere sitting above a slow, rotating surface, the two layers do not move together smoothly. Instead, there is constant interaction between them, and this interaction creates a transfer of momentum, meaning that the moving atmosphere can gradually push against the surface and influence how it rotates over time. Momentum is a simple idea in physics. It is just the measure of motion that an object carries, and when one moving system comes into contact with another, even indirectly through a dense medium like gas, part of that motion can be transferred. And over time, this transfer can build up, especially in a system like Venus, where the atmosphere is massive and continuous. On Venus, the atmosphere is not just a thin shell, it has enormous mass compared to Earth's atmosphere, and this mass is constantly in motion due to solar heating, which means it carries a significant amount of momentum as it circulates around the planet. And when this moving atmosphere interacts with the surface, it applies a very slow but continuous force across the entire planet. This force is not like a sudden push, it is more like a steady pressure that never fully stops, because the atmospheric circulation does not collapse or disappear. It continues as long as solar energy drives it, which means the surface of Venus is constantly being exposed to small but ongoing influences from above. And over long periods of time, these influences become important for the planet's rotational behavior. The surface of Venus rotates extremely slowly compared to Earth, and this slow rotation means that different parts of the surface remain under similar atmospheric conditions for long periods of time, which allows the atmosphere to maintain stable circulation patterns without being disrupted by fast surface movement. And this stability makes the transfer of momentum even more consistent. As the atmosphere moves around the planet, it drags against the upper layers of the surface through friction and pressure differences, not in a sharp or immediate way, but in a distributed way across the entire planet. And this drag acts like a brake in some regions and a push in others, depending on how the winds are flowing relative to the surface at any given time. Because the atmosphere is always in motion, this drag never stops. It is continuous, and it acts across billions of square kilometers of planetary surface, meaning even small forces become significant when applied everywhere at once and maintained for extremely long periods of time, which is exactly what happens on Venus. One of the most important aspects of this system is that the atmosphere does not just move randomly. It has a structured circulation driven by solar heating, meaning that certain patterns repeat consistently, with air rising in some regions, flowing horizontally at high altitude and descending in others, creating a global loop that redistributes energy around the planet. These large-scale circulation loops are stable enough that they persist over long time periods. And because they are stable, the momentum they carry is also stable, which means the push they apply to the surface is not random or chaotic, but follows consistent patterns that can influence rotation direction in a gradual way. On Earth, atmospheric momentum does not significantly affect planetary rotation because the atmosphere is relatively thin compared to the planet's mass, and the rotation is fast enough that any atmospheric effects are small in comparison. But on Venus, the situation is different because the atmosphere is thick, heavy, and deeply connected to the surface over long time scales, which makes its influence much more noticeable. The interaction between solar heating and atmospheric motion is the starting point of this entire explanation, because without solar energy, there would be no large-scale circulation, and without circulation, there would be no continuous transfer of momentum, and without momentum transfer, there would be no gradual influence on rotation. So every part of the system depends on the Sun providing an energy that drives atmospheric movement. As sunlight continuously heats the upper atmosphere, it creates temperature differences between different regions of Venus, especially between the side facing the Sun and the side facing away. And although the thick clouds spread and reflect much of this energy, enough variation remains to keep global wind systems active, and these systems are constantly adjusting as they move around the planet. These winds are not just surface-level movements, they extend deep into the atmosphere, forming layered circulation systems that can reach different speeds at different altitudes. And this vertical structure adds complexity to how momentum is distributed, because different layers can move at different rates while still being part of the same overall system. At higher altitudes, winds move much faster than near the surface, and this difference in speed creates shear between layers, which is another form of interaction that contributes to momentum exchange, because when layers of fluid move at different speeds, energy is transferred between them over time, gradually affecting both layers. The key idea is that Venus has a continuously moving atmosphere that is not simply reacting to the surface, but actively carrying energy and motion around the planet. And this motion is strong enough and persistent enough to interact with the surface in a way that slowly influences how the planet rotates. Even though the surface of Venus is solid rock, it is not isolated from the atmosphere above it, because the dense gas exerts pressure on every part of the surface, and this pressure is not static. It changes as winds move and circulation patterns shift, which means the surface is constantly experiencing changing forces from the atmosphere. This continuous interaction creates a long-term transfer of momentum between atmosphere and surface, and while each individual interaction is small, the effect is cumulative, building up over millions and billions of years, which is why this mechanism is considered one of the possible ways Venus's rotation could have been altered without requiring a single catastrophic event. The strength of this explanation comes from the fact that it relies on processes that are still active today, meaning we can observe atmospheric circulation on Venus right now and see that it is strong, organized, and continuous, which supports the idea that similar processes have been operating for a very long time. The atmosphere is not a passive layer sitting above Venus. It is an active system driven by solar energy that continuously moves mass around the planet. And when that mass moves, it carries momentum, and when that momentum interacts with the surface, it creates a slow but constant influence on planetary rotation that cannot be ignored when considering long timescales. This is why the atmospheric torque idea is considered a major explanation for Venus's unusual spin, because it does not rely on rare events or single moments. It relies on ongoing processes that are still happening today. Processes that are powerful enough to shape planetary behavior over long periods of time. Long-term feedback loops slowing and reversing rotation. The movement of Venus does not stay fixed once atmospheric circulation begins to dominate the planet, because the same system that creates global winds also creates long-term changes in how the planet's spin behaves. And once that motion is established, it does not remain static. It keeps interacting with the surface in a way that slowly reshapes the planet's rotation over extremely long periods of time. The atmosphere of Venus is not just moving across the surface, it is continuously exchanging momentum with it, and this exchange is not balanced in a simple way where everything cancels out. Instead, it happens in uneven patterns across different regions of the planet. Because solar heating is not uniform, and the way heat is distributed across the atmosphere changes depending on altitude, cloud density, and circulation strength. As the atmosphere flows around the planet in large-scale patterns, it does not simply slide over the surface without effect. It applies continuous pressure differences that vary depending on latitude and altitude, and these differences act like a slow turning force on the planet's outer layers, meaning that even though the surface is solid rock, it is still being influenced by a moving fluid system above it that never fully stops. Over long periods of time, this constant interaction becomes important because rotation is not just about initial formation, it is about balance between all forces acting on the planet. And when a planet has a thick atmosphere that is always moving, that atmosphere becomes one of the main forces shaping how rotation evolves. On Venus, the atmosphere is massive enough that it carries a large amount of momentum as it circulates, and when this moving mass interacts with the surface, it transfers small amounts of angular momentum through friction and pressure coupling. And angular momentum is what determines how fast and in what direction a planet spins. So even small transfers become meaningful when they happen continuously over billions of years. The key point is that this is not a short-term effect. It is a persistent process that never shuts off as long as the sun continues to heat the planet. Because solar energy is the engine that keeps atmospheric circulation active, and as long as that engine runs, the atmosphere keeps moving. And as long as it keeps moving, it keeps interacting with the surface rotation. At different layers of Venus's atmosphere, the speed of motion changes, with higher clouds moving much faster than lower layers. And this difference creates internal shear, which means layers of gas slide past each other at different speeds. And this sliding motion also contributes to how momentum is redistributed within the atmosphere before it reaches the surface. When this redistributed momentum reaches the surface, it does not arrive evenly across the planet. It arrives in patterns shaped by global circulation loops, meaning some regions receive more influence at certain times, while others receive less. But over long time scales, these variations average out into a steady overall effect that still acts on the planet's rotation as a whole. Because Venus rotates so slowly, the surface does not quickly change its position relative to these atmospheric patterns, which means the same regions of the atmosphere can interact with large areas of the surface for long periods of time, strengthening the consistency of momentum transfer and allowing small forces to build up their influence gradually. The atmosphere does not need to push the planet strongly at any single moment. It only needs to maintain consistent motion in one direction relative to the surface, and over long time scales that consistency becomes enough to influence the rotation state of the planet, especially when no other strong opposing forces are present to quickly cancel it out. This process becomes even more significant when considering that Venus does not have oceans or large surface water systems like Earth, because on Earth, oceans and land masses absorb and redistribute energy in ways that disrupt large-scale atmospheric coupling. But on Venus, there is no such buffering system, which allows atmospheric circulation to remain more stable and continuous over time. In this environment, the atmosphere acts like a dominant moving layer that is only loosely constrained by the surface below it, and this allows it to maintain strong global circulation patterns that continue regardless of small changes in surface conditions, meaning the atmosphere can keep influencing rotation without interruption. As time passes, the continuous transfer of angular momentum between atmosphere and surface gradually changes the rotation state of the planet, not in sudden jumps, but in slow adjustments that accumulate, and these adjustments can lead to a significant reduction in rotation speed compared to what would be expected from initial formation conditions. When a planet's rotation becomes slow enough, the balance between atmospheric motion and surface motion becomes even more sensitive, because the surface is no longer strongly dominant in controlling atmospheric flow, which allows atmospheric circulation to play a larger role in shaping rotational behavior over time. This is where long-term evolution becomes important, because once the system reaches a state where atmospheric influence is strong compared to surface rotation, even small imbalances in momentum transfer can continue to push the planet's rotation in a consistent direction over very long periods. Solar heating remains the constant driver behind this entire process, because without energy input from the sun, atmospheric circulation would weaken and eventually settle. But as long as energy continues to enter the system, the atmosphere remains active and continues to circulate, maintaining the conditions necessary for momentum exchange with the surface. Over billions of years, this continuous interaction can significantly alter the rotation state of a planet, especially one with a dense atmosphere like Venus, where the scale of atmospheric mass and motion is large enough to produce measurable effects on planetary rotation when integrated over time. In models that simulate Venus-like conditions, the combination of strong solar heating, thick atmospheric mass, and slow surface rotation produces a system where rotation does not remain fixed but evolves gradually as the atmosphere continues to exchange momentum with the planet. And this evolution does not require any sudden external event, only sustained internal interaction driven by solar energy. What makes this process important is that it does not depend on rare or extreme conditions. It depends on ongoing physical processes that are already present on Venus today, meaning the same atmospheric circulation patterns that exist now are part of a long-term system that has been active for an extremely long time. The atmosphere and the surface are not independent systems. They are connected through continuous physical interaction, and this connection allows energy and momentum to move between them in a way that slowly reshapes planetary rotation without requiring any abrupt change. As this interaction continues, the planet can move through different rotational states, with changes in speed and direction emerging gradually as the balance of forces shifts over time. And in some cases, this can lead to a full reversal of rotation if the cumulative effect of atmospheric torque is strong enough over long periods. This is why Venus is often described as a planet where rotation may not have been set once and left unchanged, but instead shaped continuously by the interaction between its thick atmosphere and solar energy, with the final result being the slow and reversed rotation observed today. Solar tides and long-term spin evolution. Venus does not exist in isolation. It is constantly under the influence of the Sun, and that influence is not only about light and heat, it is also about gravity, because the Sun is massive enough to pull on every part of Venus at the same time, and this pull is not exactly equal across the planet, which creates what scientists call tidal forces. And these forces are slow, steady, and always present, acting over timescales so long that they are almost invisible in the short term but extremely important when you look at billions of years of planetary evolution. To understand solar tides, you first need to picture how gravity works across a large object like a planet. Because the Sun does not pull on Venus as a single point, it pulls slightly more strongly on the side of Venus that is closer to it, and slightly less strongly on the side that is farther away. And this difference is very small in any single moment, but it is always there, always acting, never turning off, and over long periods of time, this uneven pull creates a stretching effect across the planet. On Earth, this same type of force is responsible for ocean tides, where the Moon and the Sun pull on Earth's oceans and create rising and falling water levels. But Venus does not have oceans, so the effect does not show up in visible water movement. Instead, it acts on the solid body of the planet and its thick atmosphere, slowly creating internal stresses and small shifts in motion that affect rotation over extremely long timescales. These solar tides act like a braking force on planetary rotation, not in a sudden way, but in a gradual way, where the planet's spin is constantly being slightly slowed by gravitational interaction with the Sun. Because as Venus rotates, different parts of the planet move closer to and farther from the Sun, and this continuous change creates friction-like effects inside the planet's structure that resist motion and slowly remove rotational energy. This loss of rotational energy does not disappear instantly. It is transferred into heat and internal deformation, meaning that over time the planet's spin can gradually slow down. And if there are no strong opposing forces, this slowing effect continues steadily over billions of years, shaping how the planet rotates long after its formation. To understand why this matters for Venus, it helps to compare it with Mercury, another planet close to the Sun that also experiences strong tidal forces, because Mercury shows a very different but related behavior, where instead of freely rotating like Earth or slowly reversing like Venus, it has become locked into a spin-orbit resonance, meaning its rotation is directly linked to its orbit around the Sun in a stable ratio. Mercury rotates 3 times for every 2 orbits around the Sun, which creates a predictable pattern where certain parts of the planet face the Sun repeatedly at regular intervals. And this happens because solar tides slowly shape Mercury's rotation over time until it reached a stable balance point where the gravitational forces and rotational motion settled into a consistent pattern that does not change easily. This process is called tidal locking in a broader sense, and it shows how strong solar gravity can influence planetary rotation over long periods, because it takes a rotating body and gradually adjusts its spin until it reaches a stable configuration where the gravitational pull from the Sun is balanced by the planet's rotation and orbital motion. On Mercury, this process resulted in a stable resonance rather than a complete stop or reversal of spin, because the conditions of its mass, distance from the Sun, and initial rotation speed led to a balance point that favoured a specific rotational ratio, and once that state was reached, it became stable over time. Venus is different from Mercury in important ways, but the underlying principle of solar tides still applies, because Venus is also close to the Sun and experiences strong gravitational gradients across its surface, meaning the same kind of slow braking force has been acting on it since early in its history. However, Venus does not show a simple spin-orbit resonance like Mercury, which means that while solar tides are clearly acting on it, they have not produced a neat lock pattern. Instead, they appear to have contributed to a much more complex rotational evolution that includes extremely slow rotation and reverse direction. The key idea behind solar tides acting on Venus is that as the planet rotates, the Sun's gravity constantly pulls more strongly on the near side than the far side, and this creates a slight distortion in the planet's shape. A stretching effect that does not disappear immediately, but instead lags slightly behind the planet's rotation. And this lag creates a torque, which is a twisting force that slowly affects how the planet spins. This torque always works in a direction that tries to reduce rotational energy, meaning it acts like a brake on the planet's spin. And over long periods of time, this braking effect can significantly slow down rotation, especially if there are no strong forces maintaining a fast spin. In Venus's case, the rotation is already extremely slow, which means that solar tides have had a very long time to act on the planet without being countered by strong rotational stability. And this allows the tidal braking effect to operate continuously over billions of years, gradually shaping the rotation state we observe today. The interaction between solar tides and planetary rotation is not just about slowing down spin, it is also about how energy is redistributed inside the planet, because as the planet deforms slightly under gravitational stress, internal friction generates heat, and this heat is lost over time, which means rotational energy is being steadily converted into thermal energy, reducing the overall spin rate. This process is extremely slow on human timescales, but over geological timescales it becomes significant, because even tiny changes in rotational speed, when applied continuously over billions of years, can lead to major differences in final rotation state compared to initial conditions. One important detail in this process is that solar tides do not act equally on all rotation speeds, because the strength of tidal effects depends on how fast the planet is rotating relative to its orbital motion, meaning that as the rotation slows down, the balance of forces changes, and the tidal influence can shift in how it affects the planet's motion. On a fast rotating planet, tidal forces may act in one way, while on a slow rotating planet like Venus, the same forces can behave differently, creating more complex interactions between rotation and orbital motion that do not simply lead to a single, predictable outcome. This is why solar tides alone do not fully explain Venus's current rotation, but they are still a major part of the long-term evolution, because they provide a continuous force that works alongside other processes, shaping how the planet's spin changes over time rather than acting as a one-time event. When comparing Venus and Mercury again, the difference becomes clearer, because Mercury reached a stable resonance where tidal forces and orbital motion aligned into a consistent pattern, while Venus did not settle into a simple resonance, which suggests that other factors were influencing its rotation at the same time, preventing it from locking into a stable tidal state like Mercury did. This difference is important because it shows that solar tides are powerful, but not always decisive on their own. They interact with other forces, such as atmospheric dynamics and past collision events, and the final rotation state of a planet depends on how all these forces combine over time. In Venus, the presence of a thick atmosphere adds another layer of complexity, because while solar tides act on the solid body of the planet, the atmosphere also responds to solar heating and internal circulation, meaning there are multiple systems interacting with each other under the same gravitational environment. Even without fully combining all these effects, solar tides remain one of the most consistent long-term influences on Venus, because unlike impacts or short-term events, tides never stop. They continue acting as long as the Sun and planet exist in their current configuration, slowly shaping rotation in a persistent way that accumulates over time. This makes solar tides an essential part of understanding how Venus reached its current spin state, because they provide a background force that continuously modifies rotation, even if other processes are responsible for larger changes or more dramatic shifts in direction. Possibility of stable retrograde equilibrium state. Over very long stretches of time, solar tides do not just slow a planet down in a simple straight line. They keep acting in a steady way that slowly reshapes how the planet's rotation behaves as a whole. And when you stretch this idea across billions of years, the result is not a sudden change, but a gradual shift in balance, where different forces keep adjusting the spin state in small steps until the planet reaches a stable configuration that can last for an extremely long time without breaking. On Venus, this long-term tidal influence has had more than enough time to act, because the planet is ancient, and from the moment it formed, the Sun's gravity has been pulling on it unevenly, creating a constant twisting effect that never stops. And even though each individual pull is small, the key detail is that it is continuous, meaning there is no pause, no reset, and no return to a neutral state, only constant pressure acting on a rotating body over immense time. As Venus rotates, different parts of its structure are always slightly stretched by the Sun's gravity, and this stretching is not perfectly aligned with the planet's shape, because the planet is rotating at the same time as it is being pulled, which creates a small offset between where the strongest gravitational pull happens and where the planet's material actually bulges. And this offset is what creates a torque, a slow turning force that gradually modifies the rotation. This torque does not behave the same way at all rotation speeds, because when a planet spins quickly, the offset between the tidal bulge and the direction of the Sun's pull behaves differently compared to when a planet spins very slowly. And on a planet like Venus, where rotation is already extremely slow, this interaction enters a different regime, where the balance between spin and tidal distortion becomes more sensitive to small changes. As the rotation slows further under tidal influence, the planet becomes more vulnerable to other small forces, because a fast rotating planet has strong angular momentum that resists change, but a slow rotating planet has much less resistance, meaning that even weak continuous forces can have a noticeable effect over time. And this is where the long-term evolution becomes important, because Venus is not in a fast, stable spin state. It is in a slow, evolving one, where changes can accumulate more easily. In this slow regime, the Sun's tidal forces do not simply act as a brake in a single direction. They interact with the planet's changing rotation in a more complex way, because the direction and strength of the tidal torque depend on how the planet is spinning relative to its orbit. And as that relationship shifts, the way energy is transferred also shifts, creating a moving balance rather than a fixed one. This is where the idea of equilibrium states becomes important, because a planet under continuous tidal influence does not just keep slowing forever in a simple way. Instead, it can settle into specific rotational states where the forces acting on it reach a kind of balance, where the torque from tides no longer causes large changes in rotation, and the system becomes stable over long time scales. Mercury is an example of this kind of outcome, where solar tides shaped its rotation into a stable resonance with its orbit. And once that balance was reached, the system became locked into a predictable pattern that does not easily change, because the gravitational forces and rotation are aligned in a stable configuration. Venus, however, does not fit into the same simple pattern, because instead of settling into a clean resonance, its rotation ended up extremely slow and reversed, which means that if tidal forces played a major role, they did not lead to a simple locking process, but instead interacted with other influences in a way that produced a more complex final state. One possible way to understand this is that Venus may have passed through multiple rotational stages over time, where solar tides gradually slowed its original spin. But as the rotation became weaker, the system became more sensitive to other forces, and small differences in how momentum was transferred between layers of the planet could have influenced the final direction of spin. In this kind of evolving system, rotation is not controlled by a single dominant factor, but by a competition between different effects, where solar tides continuously remove rotational energy, while other processes can redistribute or reshape that energy in ways that change how the slowdown progresses over time. As the planet's rotation weakens, the tidal influence of the Sun becomes relatively more significant compared to the planet's own angular momentum, which means that the same gravitational pull has a stronger effect on a slow rotating planet than it would on a fast one. And this changing relationship allows the system to move toward different rotational outcomes depending on the exact conditions at each stage of evolution. Over extremely long timescales, this evolving balance can lead to states where rotation becomes not just slow, but fundamentally different in direction compared to the original spin, especially if other consistent forces are acting alongside tides. Because once the system is no longer strongly anchored by fast rotation, it becomes easier for cumulative effects to shift the final outcome. This does not happen quickly, and it does not require a single dramatic event. Instead, it is the result of many small adjustments that build on each other, each one slightly changing the rotation state until the planet reaches a configuration that is stable under the combined influence of all forces acting on it. In this sense, solar tides act like a long-term shaping mechanism, not by forcing a specific outcome directly, but by continuously removing energy from rotation and allowing the system to explore different states over time until it finds a stable configuration that fits the balance of forces present in the environment. What makes this especially important for Venus is that its thick atmosphere adds another layer of interaction on top of tidal effects, because while solar gravity acts on the solid planet, the atmosphere responds directly to solar heating and circulation patterns, meaning that there are two moving systems interacting with the same external influence, and both are evolving over time. Even though tides alone cannot fully determine the final rotation state, they provide a constant background influence that shapes how other processes unfold. Because without tidal braking, a planet might retain a faster rotation for much longer. But with tidal forces acting continuously, the system is pushed towards slower and more sensitive rotational states where other influences become more important. When viewed across billions of years, the combination of solar tides and internal planetary response creates a slow evolutionary path for rotation, where the planet does not remain fixed in its original spin, but gradually shifts as energy is removed and redistributed through internal and external interactions. In this long timescale view, Venus is not a static object with a single fixed rotation history, but a system that is being continuously adjusted by gravitational forces from the Sun, slowly changing its spin behavior as it moved through different stages of stability, each stage influenced by the balance between tidal forces, internal structure, and atmospheric dynamics acting together without interruption. What Venus might have looked like in the past. To understand Venus today, with its extreme heat, thick clouds, and strange rotation, it is not enough to only look at what it is now. Because planets do not start in their final state, they go through long changes over billions of years. And Venus is one of the clearest examples of a world that may have started in a very different condition before slowly shifting into what we see today. And to build that picture, scientists work backward from data, using physics, atmosphere models, and comparisons with Earth to imagine what early Venus could have been like when the solar system was still young and the planets were still forming their final structure. In the early solar system, Venus would have formed in the same general region of space as Earth, from the same rotating disk of gas and dust, and this already tells us something important. because objects forming in the same region tend to share similar building materials, meaning Venus likely started with a rocky surface made of silicate materials, along with a mix of volatile compounds that were present in the inner solar system at that time. And early in its history, there is a strong possibility that its surface conditions were not as extreme as they are today. At that early stage, Venus may have had a rotation speed that was much faster than it is now, because planets tend to rotate more quickly during formation due to the angular momentum gained from repeated collisions of growing bodies, and this early spin would have been shaped by many impacts from smaller objects still moving through the inner solar system, each one adding or adjusting rotation depending on angle and speed, creating a dynamic and changing spin state rather than a fixed one. In this early phase, Venus likely had a more Earth-like rotation pattern, meaning it may have rotated in a direction similar to Earth's current spin, because that is the natural outcome of forming in a shared rotating disk, and unless a major disturbance occurs, planets tend to keep that inherited direction, at least in their early stable stages, before long-term forces begin to reshape their motion. If Venus had a faster early rotation, this would have had a major effect on its climate, because rotation speed plays a direct role in how heat is distributed across a planet's surface, and on a fast rotating planet, heat from the Sun is spread more evenly between day and night sides, preventing extreme temperature differences from building up too strongly in one location. And this helps create more balanced atmospheric circulation patterns. With a faster spin, Venus could have had a more active cycle of winds, clouds, and surface heating patterns that moved energy around the planet in a way that prevented one side from becoming permanently extreme. And this kind of circulation can support more stable climate conditions, especially if the atmosphere contains gases that allow heat to move efficiently across the planet. There is also a strong possibility that early Venus had liquid water on its surface, at least for a period of time, because models of early solar system conditions suggest that inner planets may have received enough water delivery from asteroids and comets to form oceans, and Venus's size and position in the solar system would have allowed it to maintain surface temperatures within a range where liquid water could exist, at least before stronger greenhouse effects took over. If liquid water existed on early Venus, it would have played a major role in shaping climate stability, because water is extremely effective at absorbing and redistributing heat, and large bodies of water act as thermal buffers that prevent extreme temperature swings, which helps stabilize atmospheric conditions and supports more uniform weather patterns across the planet's surface. In such a scenario, early Venus would not have looked like the extreme world it is today. Instead, it may have been a much more active and dynamic planet with oceans, cloud systems driven by water vapor, and weather cycles that moved energy between surface and atmosphere in a way that was closer to early Earth, even though differences in distance from the Sun and atmospheric composition would still create important distinctions between the two planets. Rotation plays a key role in how such a climate behaves, because a planet's spin determines how quickly sunlight moves across its surface, and this controls how long any given region stays in daylight or darkness, which directly affects temperature distribution, wind patterns, and the formation of atmospheric circulation cells. And on a faster rotating Venus, these patterns would have been more complex and more evenly distributed compared to the slow rotation state it has today. On Earth, rotation creates a balance where the atmosphere is divided into large circulation zones that move heat from the equator toward the poles, and similar patterns would likely have existed on early Venus. But the exact structure would depend on how fast Venus was rotating at that time, and even small differences in rotation speed can significantly change how winds and storms behave across a planet. If Venus had oceans in its early history, the interaction between ocean currents and atmospheric circulation would have added another layer of complexity, because oceans move heat slowly but steadily across long distances, and when combined with atmospheric winds, they create a feedback system that helps stabilize climate conditions over long periods, reducing extreme variations and supporting more balanced energy distribution across the planet. This kind of system would also influence long-term rotation behavior indirectly, because atmospheric and oceanic circulation patterns can transfer momentum between different parts of a planet. And while these effects are usually small compared to gravitational forces, over long timescales they can contribute to subtle changes in rotation speed and stability, especially when combined with other influences, such as solar heating and internal planetary dynamics. Even though early Venus may have had more Earth-like conditions, it would not have been identical to Earth, because small differences in distance from the Sun, atmospheric composition, and initial formation conditions would still create distinct climate behavior, and these differences could slowly grow over time as the planet evolved, especially if certain feedback processes began to strengthen atmospheric density or alter heat retention in the atmosphere. Rotation also affects how stable a planet's climate remains over time, because faster rotation tends to distribute heat more evenly, while slower rotation allows stronger temperature differences between day and night sides. And these differences can lead to stronger atmospheric circulation patterns that move energy in more concentrated ways, which can eventually influence the long-term evolution of both climate and rotation together. In early Venus, if rotation was faster, the climate system would likely have been more balanced, but as time passed, small changes in atmospheric composition and solar energy absorption could have gradually altered this balance, slowly changing how heat was distributed across the planet and how atmospheric circulation behaved, setting the stage for long-term changes in rotation behavior. At this stage of Venus's history, nothing would have been fixed in its final form. Everything would still be evolving, with rotation, atmosphere, and surface conditions all interacting continuously, shaping each other over time. And small changes in one system could influence the others in ways that build up slowly over millions or billions of years. This is why early Venus is often described not as a static version of the planet we see today, but as a developing system where conditions could have been significantly different, possibly including liquid water, faster rotation, and more Earth-like climate patterns, even though all of these conditions would eventually change as the planet continued to evolve under the influence of solar energy, atmospheric processes, and long-term gravitational effects. Runaway greenhouse effect. As time moved forward in Venus's early history, the conditions on the planet did not stay stable, because planets do not hold one fixed state for long periods without change. They constantly respond to what is happening around them and inside them. And Venus was no different, even if the changes happened so slowly that no single moment would have looked dramatic on its own. Only the long chain of small shifts would eventually create a completely different world from what may have existed at the beginning. One of the most important shifts involves how the atmosphere behaves as it becomes thicker and more active over time. Because even if early Venus had conditions that supported oceans or a more Earth-like climate, the atmosphere would still be exposed to continuous solar energy from the Sun. And that energy does not just warm the surface, it drives chemical reactions, evaporation cycles, and large-scale movement of gases. And when these processes continue for long enough, they can begin to change the overall structure of the atmosphere itself. As solar energy enters the atmosphere, it interacts with gases and surface materials. And over long periods, this interaction can lead to gradual changes in atmospheric density and composition, especially if certain gases are more easily retained or released depending on temperature. And once these changes begin, they can slowly shift the balance of how heat is trapped and distributed around the planet. When the atmosphere becomes denser, it starts to play a much larger role in shaping surface conditions, because a thicker atmosphere holds more heat and moves more energy through circulation, which increases the strength of global wind systems. And these winds are not random or isolated. They form organized patterns that can cover the entire planet, driven by differences in heating between regions exposed to more sunlight and those receiving less. These circulation patterns do not stay fixed in one form. They adjust as atmospheric composition changes, and as they adjust, they can begin to influence the surface in stronger ways, because a denser atmosphere carries more mass in motion, and that mass exerts pressure on the surface as it flows, meaning that over time, the connection between atmosphere and surface becomes more significant. At the same time, solar energy continues to act on the planet without interruption, and this constant input of energy ensures that atmospheric motion does not stop. Instead, it keeps being renewed, meaning that circulation systems remain active and continue to transfer energy across the planet, maintaining a persistent movement pattern that interacts with the surface rotation. As these changes continue, the original rotation of Venus does not remain unchanged, because rotation is not independent from atmospheric behavior, especially on a planet where the atmosphere is becoming increasingly dense. And when the atmosphere becomes more influential, it begins to interact more strongly with surface motion, which can gradually alter how fast the planet spins. This interaction does not require a sudden external event. It happens through continuous contact between moving air and the rotating surface, where pressure differences and friction-like effects slowly transfer small amounts of motion between the two systems. And while each individual transfer is extremely small, the process never stops, which allows changes to accumulate over long periods of time. As atmospheric density increases, the effectiveness of this momentum transfer also increases, because a thicker atmosphere carries more moving mass, and more mass in motion means a stronger ability to influence the surface beneath it, which makes the rotational state of the planet more sensitive to atmospheric circulation than it would be on a planet with a thinner atmosphere. Over long timescales, this growing influence can begin to reshape the balance of forces acting on rotation, because the planet is no longer only responding to its initial spin and gravitational conditions, it is also responding to a constantly moving atmospheric system that is being driven by solar energy and internal circulation processes. And this adds a new layer of complexity to how rotation evolves. If early Venus had oceans, the loss or redistribution of those oceans over time would also play a role in this transition. Because water acts as a stabilizing force in climate systems, and changes in water distribution can affect how heat is absorbed and released, which in turn influences atmospheric movement, and when atmospheric movement changes, the forces acting on rotation also change. As atmospheric density continues to increase and circulation becomes more powerful, the difference between early and later Venus conditions becomes more noticeable, because the planet gradually shifts from a more balanced climate system into one where the atmosphere dominates the surface environment. And this shift changes how energy is transferred across the planet as a whole. In this evolving system, the surface is no longer the main driver of atmospheric behavior. Instead, the atmosphere becomes the dominant moving layer, and the surface becomes more responsive to atmospheric motion, which creates a situation where rotation is influenced more by atmospheric dynamics than it was in earlier stages. At the same time, solar energy continues to provide a constant driving force, ensuring that atmospheric circulation remains active, and as long as this energy input continues, the system does not settle into a simple fixed state. It continues to evolve, with gradual changes in atmospheric structure and surface interaction shaping the planet's rotation over long periods. As these long-term changes accumulate, Venus moves further away from its early state, and even though the changes are slow, they are persistent. And persistence is what matters over geological timescales, because small changes that repeat continuously eventually become large transformations when given enough time. This is why Venus cannot be thought of as a planet that simply formed and stayed the same until today. Instead, it must be understood as a planet that has gone through continuous evolution, where atmosphere, surface, and solar influence have all played a role in shaping its final state, and where even the rotation of the planet is part of that long evolving system rather than a fixed property set at formation. Computer simulations and modern research. Modern understanding of Venus no longer depends only on telescopes or simple observations, because the problem of its strange rotation is too complex for direct observation alone. Instead, it depends heavily on computer models that try to rebuild the planet's entire history, step by step, using physics, chemistry, gravity, and atmospheric behavior all working together in one system. And these models are the closest thing scientists have to a controlled way of testing what might have happened to Venus over billions of years without actually being able to go back in time. These simulations begin with basic physical rules, mainly gravity, motion, heat transfer, and fluid dynamics. And then they apply those rules to a virtual early solar system where planets are still forming, still colliding, and still changing their rotation states. And in these early stages, Venus is treated as a growing body inside a chaotic environment filled with other large objects that can interact through repeated gravitational encounters and occasional high-energy impacts. In N-body simulations, every object is treated as having its own gravity, meaning each body pulls on every other body in the system. And over time, these interactions create complex orbital paths where planets and smaller bodies shift positions, sometimes collide, sometimes merge, and sometimes exchange angular momentum. And this exchange is especially important for understanding rotation, because spin direction and spin speed are both directly tied to how momentum is distributed during these early interactions. When a large impact occurs in these simulations, the model tracks how energy and angular momentum are transferred, and depending on the angle and speed of the collision, the resulting planet can experience changes ranging from minor tilts to major spin alterations, including cases where rotation slows dramatically or even reverses direction if the incoming momentum is strong enough and aligned in a specific way relative to the planet's original spin. These early solar system models show that chaotic interactions are not rare. They are expected, because the early environment was full of leftover material from planetary formation, and that material did not disappear immediately. Instead, it continued to move through the system for long periods, interacting with forming planets and contributing to their final spin states through repeated gravitational and physical interactions. But rotation is not determined by impacts alone, which is why modern simulations also include climate and atmospheric modeling, where the planet is treated not only as a solid rotating body, but also as a system with a dynamic atmosphere that responds to heat, pressure, and radiation from the sun. And this is where climate rotation coupling becomes important, because the atmosphere and surface do not behave independently. They influence each other continuously over time. In climate rotation models, the atmosphere is divided into layers with different temperatures and pressures, and solar energy is applied to simulate how heat moves through these layers, creating circulation patterns that resemble global wind systems. And these winds are then allowed to interact with the surface rotation of the planet, which allows scientists to test how atmospheric motion can influence spin over long periods of time. These models show that atmospheric behavior can become a significant factor in rotation evolution when the atmosphere is dense enough and the rotation is slow enough, because under those conditions the transfer of momentum between atmosphere and surface becomes more effective, and small continuous forces can accumulate into larger changes in spin behavior over geological timescales. What makes Venus especially difficult to model is that it combines multiple extreme conditions at the same time, including a very thick atmosphere, very slow rotation, high surface temperatures, and strong solar radiation input. And each of these factors influences the others, meaning that any realistic simulation must account for a tightly connected system where changing one variable affects all others in complex ways. Because of this complexity, no single simulation can fully reproduce Venus's history with complete certainty. Instead, researchers run many different models with slightly different starting conditions, such as different initial rotation speeds, different atmospheric densities, different impact histories, and different solar energy levels. And then they compare the results to see which combinations come closest to matching the present state of the planet. Even with modern computing power, these simulations face limits because the timescales involved are enormous, stretching across billions of years, and the level of detail required to simulate both atmospheric circulation and planetary rotation simultaneously over such long periods is extremely high, which means scientists often have to simplify certain parts of the system to make calculations possible. And these simplifications can affect how accurately the results reflect reality. Despite these challenges, the models consistently show one important result, which is that Venus's current rotation state is not easy to produce through a single process alone. Instead, it usually requires a combination of factors, including early chaotic impacts, long-term solar tidal forces, and continuous atmospheric interaction, all contributing in different ways over different time periods. This is where the uncertainty becomes important, because even though models can reproduce parts of Venus's behaviour, they do not yet fully agree on how all the processes fit together into a single continuous history. Meaning, there is still no complete simulation that explains every aspect of Venus's rotation, atmosphere, and surface conditions at the same time in perfect detail. Space missions are essential for solving these gaps, because while simulations can test ideas, they still rely on real data to confirm what is actually happening on the planet. And Venus is difficult to study directly because its surface is hidden under thick clouds that block most optical observation, making it impossible to see the surface directly using normal telescopes. This is why radar mapping has been so important in the past, because missions like NASA's Magellan spacecraft used radar to map the surface of Venus through its clouds, revealing detailed information about its topography and rotation. And this data helped refine models of how fast the planet spins and how its surface is structured. But even this information is not enough to fully explain its rotational history. New missions are being developed to improve this understanding further, including NASA's Veritas mission, which aims to create higher resolution maps of Venus's surface and study its geological history in more detail, and ESA's Envision mission, which will focus on understanding the relationship between Venus's surface and atmosphere by combining radar imaging with atmospheric measurements to build a more complete picture of how the planet behaves as a system. Another important mission is Da Vinci Plus, which is designed to study Venus's atmosphere directly by sending a probe through it, collecting data on its composition, structure, and chemical behavior as it descends, which will help scientists understand how the atmosphere has evolved over time and how it interacts with the surface in ways that might influence rotation and long-term planetary behavior. Even with these missions planned, there are still major unknowns that remain unresolved, especially regarding how Venus transitioned from a potentially more Earth-like early state into its current extreme environment, and how exactly its rotation became so slow and reversed, because current models can reproduce parts of this evolution, but not all of it in a single consistent framework. One of the biggest missing pieces is the exact timeline of atmospheric changes, because while it is known that Venus has a very thick atmosphere today, the rate at which it became this thick and the stages it went through during that process are still not fully understood, and this makes it difficult to link atmospheric evolution directly to changes in rotation. Another missing piece is the precise role of early impacts, because while simulations show that large collisions can alter rotation significantly, there is still uncertainty about how many such impacts Venus experienced and how they combined with other processes over time, making it hard to determine whether a single major event or multiple smaller events played the dominant role. There is also uncertainty in how exactly atmospheric circulation interacts with solid body rotation at deep levels, because while upper atmosphere behavior is well observed, the deeper coupling between atmosphere and surface over long timescales is still not fully measured, and this limits how accurately models can simulate momentum transfer between layers. Because of all these gaps, modern research continues to produce different possible histories for Venus, rather than a single agreed explanation. And each new model tends to explain some aspects better than others, but none yet explain everything at once in a fully complete way. This is why Venus remains one of the most difficult planets to understand in terms of rotation, because even with advanced simulations, spacecraft data, and long-term theoretical models, the system is still too complex to reduce into a single clear pathway. And the best current understanding is that multiple processes must have worked together over time, even though the exact balance between those processes is still not fully known. Competing ideas and unresolved questions. Venus remains one of the most difficult planets to fully explain when it comes to rotation, not because scientists lack data, but because the data does not point to a single clean story. Instead, it points to multiple possible processes that may have worked together over very long periods of time, And the challenge is that each process can explain part of the situation. But no single process can explain everything at once in a complete way that matches all observed features of the planet. One of the biggest open questions is whether Venus experienced one giant impact or many smaller impacts during its early history, because both possibilities can change rotation but in different ways, and each leaves different traces in a planet's final structure and motion. So understanding which scenario is more accurate is important for building a full history of Venus's spin evolution. A single giant impact would mean that at some point in Venus's early formation, a large object struck the planet with enough force to significantly alter its rotation, possibly slowing it, tilting it, or even reversing it depending on the direction and energy of the collision. And this kind of event would create a clear turning point in the planet's rotational history, after which slower long-term processes would take over. Multiple smaller impacts, on the other hand, would mean that Venus's rotation was not changed in one sudden moment, but gradually adjusted over time through repeated collisions with smaller bodies, each one adding or removing small amounts of angular momentum, slowly reshaping the planet's spin direction and speed through accumulation rather than a single dramatic shift. Both scenarios are physically possible based on what is known about early solar system conditions. Because the inner solar system was not empty during planetary formation, it was filled with leftover material, and growing planets regularly interacted with this material, meaning collisions of different sizes were likely common events during the early stages of planetary development. Another major question is whether Venus ever rotated quickly in a way similar to Earth, because most models of planetary formation suggest that young planets tend to spin relatively fast due to the angular momentum gained during accretion. And if Venus followed this pattern, then its current extremely slow rotation would require significant changes over time to explain how it moved from a fast spin state to the present slow and reversed rotation. Some models suggest that early Venus may have had a faster rotation period, possibly similar to Earth or even faster, and that over time, this rotation was gradually reduced by a combination of tidal forces and atmospheric interactions, while other models suggest that Venus may have started with a slower or more irregular spin, depending on how its formation and early collisions unfolded, meaning the starting point itself is still uncertain. The question of how stable Venus's current retrograde rotation is also important, because once a planet reaches a certain rotational state, it can remain stable for long periods if the forces acting on it are balanced. But if the system is still evolving, then small changes in atmospheric behavior, solar influence, or internal dynamics could continue to modify rotation even today. Current understanding suggests that Venus's retrograde rotation is relatively stable under present conditions, meaning it does not appear to be rapidly changing direction or speed in a way that would suggest an imminent shift. But this stability does not mean the system is simple. It only means that the current balance of forces has settled into a long-lasting configuration. Another major question is why Venus is the only inner planet with a full retrograde rotation. Because Mercury rotates very slowly, but still in the same direction as its orbit, Earth rotates normally with a stable prograde spin, and Mars also follows a standard prograde rotation, which makes Venus stand out as a clear exception among the inner planets. This uniqueness suggests that Venus experienced a different combination of events or long-term processes compared to its planetary neighbours, even though all inner planets form from the same general protoplanetary disk, meaning small differences in early conditions or evolutionary history may have led to very different final outcomes in rotation state. One possibility is that Venus experienced a specific combination of early impacts and long-term tidal effects that did not occur in the same way for the other planets, and that this combination pushed it into a unique rotational path, while Mercury reached a different equilibrium state due to its smaller size and closer proximity to the Sun, and Earth and Mars maintained more stable rotation due to different balances of internal and external forces. Another open question is whether similar rotational reversals could happen on exoplanets, because if the processes that shape Venus are not unique to the solar system, then planets in other star systems with thick atmospheres, strong stellar radiation, and long-term tidal interactions could potentially experience similar changes in rotation over time. Current models suggest that atmospheric torque, tidal forces, and collision history are not unique to Venus, meaning they could occur in other planetary systems as well, especially in planets located close to their stars, where tidal forces are strong and atmospheric heating is intense. But whether full rotation reversal is common or rare remains uncertain because direct observational data from exoplanets is still very limited. What makes Venus particularly important in this context is that it provides a real example of extreme rotational evolution, showing that a planet can move far away from expected spin behavior under the influence of long-term physical processes, which helps scientists understand that planetary rotation is not always fixed or simple, but can evolve in complex ways depending on environmental and historical conditions. When all current evidence is combined, the most consistent scientific interpretation does not rely on a single cause. Instead, it points towards a combination of multiple processes working together over long timescales, including early impacts that may have altered initial rotation, solar tidal forces that continuously removed rotational energy, and atmospheric dynamics that gradually transferred momentum between layers of the planet. This combined view suggests that Venus's rotation is not the result of one isolated event, but the outcome of a long evolving system where different physical processes interacted continuously, each contributing in different ways at different stages of planetary history, shaping the final state we observe today. In this framework, Venus's rotation is better understood as a long-term system result rather than a single cause mystery, meaning that no single explanation is sufficient on its own, and the full picture only emerges when multiple physical processes are considered together across billions of years of evolution. What Venus demonstrates more broadly is that planetary rotation is not always stable or simple. It can be reshaped by a combination of internal structure, atmospheric behavior, gravitational forces, and early formation history. And even small differences in these factors can lead to dramatically different outcomes across planets that formed in the same region of space. This makes Venus an important case for understanding planetary evolution in general because it shows that rotation is not just a fixed property set during formation, but a dynamic feature that can continue to change long after a planet has formed, depending on how different forces interact over time. Future space missions and improved computer models are expected to refine this understanding further, because better data on Venus's atmosphere, surface structure, and internal composition will help reduce uncertainty in current models and allow scientists to test which combinations of processes are most likely responsible for its present rotation state. As more detailed measurements become available, especially from upcoming missions focused on radar mapping and atmospheric entry probes, existing models may be adjusted, refined, or even replaced, leading to a clearer understanding of how Venus evolved and how its unusual rotation developed over time under the influence of multiple interacting physical processes.